In this video, I want to give you an intuitive understanding of the policy gradient theorem. This is the underlying idea behind the many policy gradient methods that are used to train AIs. Some examples of AIs that have been trained using some form of policy gradients are AlphaStar, the AI trained by DeepMind to play StarCraft 2, and it eventually got so good that it could beat professional StarCraft players. Another example is the AI trained by OpenAI to play Dota, and it also eventually got so good that it could beat professional Dota players.
GG is called an OpenAI take game one.
And another example from robotics is the robotic hand that OpenAI trained to be able to solve a Rubik's Cube, and it could solve it with just a single hand, which is a really impressive feat of dexterity, especially for a robotic hand. So when I first learned about the policy gradient theorem, I learned it in a way that looks similar to this. And this is OpenAI's Spinning Up in DeepRL, their website. It's a great resource for learning about reinforcement learning. And here they give a nice, concise derivation of the basic policy gradient theorem. And it usually looks like this. You're trying to find the gradient of the expected return, and you go through multiple mathematical steps and eventually end up with something down here, which you can use to estimate the gradient so that you can improve your policy. And this is how I initially learned it, and I thought I understood what was happening, but it wasn't until later, until I actually worked through an example and tried to derive this equation myself just by thinking about how I'd improve the policy. And after that, I felt like I had a much better understanding. So in this video, I want to walk you through those steps that I took and kind of guide you into how we can come to this same conclusion as this equation does, but hopefully end up with a kind of better picture in our head of what we're actually calculating. So we're going to start off by analyzing this little game I came up with where we are this robot, and it's a very simple game just to make it easy to study, where we only have 4 positions, 0, 1, 2, and 3. We're starting off in this position number 2, and we only have 2 options. We can either choose to go left or go right. So if we choose to go right, we'll end up at the flag. We'll get a reward of +10, and this will end the episode or the game, however you want to say it. So the flag is a terminal state. Now, if we go left, we'll pick up the diamond, which will give us a reward of +3, and then we'll end up on this little slope over here, where we can again choose to go left or right, but the game hasn't ended in this state. And from here, if we choose to go left, we end up in the fire pit. Wah, wah. And we get a reward of -10, and that ends the episode. So the fire pit is also a terminal state. However, if we choose to go right from this position, there's a 90% chance we'll make it back up on top of the hill. However, there's a 10% chance that we'll slip on our way trying to go up the hill and end up back in the fire pit. Now, if we make it back up on the hill, that'll give us a reward of 0. It's kind of like a bypass state. And then we'll have the option of making another choice from this state. We can choose to go right or left. If we go left, we'll end up back on the side of the hill, and this will actually end the game. Just to make it simple, I made it so that after 3 steps, the game ends no matter what, and this would be our 3rd step. However, if from here we choose to go right, we'll end up back at the flag, getting a reward of +10, and then the game will be over. So if we look at this game in a tree structure, it looks something like this. We start off in this state, and we can go right or left. If we go right, we end up at the flag, and that will end this episode, this run of the game. And if we go left, we'll end up on the hill over here. From here, if we go left, we'll end up in the fire pit. However, if we go right, we'll have a 90% chance of making it back up on top of the hill and a 10% chance of slipping and falling back in the fire pit. And once we're back up on the hill, we can either go left to end up on the side of the hill or go right to make it to the flag and get the final reward of +10. So you'll see the rewards we'll get in each state in these green boxes here. And over on the right side of this state diagram, you'll see some text. And this is usually the kind of information we'll be working with when we're doing a reinforcement learning problem. So we'll start off by getting an observation, which will often be just a list of numbers, usually floating point numbers, but I just made them integers in this example to keep it simple. And in this example, our observation is going to be 2 values. The first number is our position, so 0, 1, 2, or 3. We're starting off in position 2. And the second number is whether a diamond exists in the environment or not. So right here it's 1 because the diamond exists. However, if we go left and pick up the diamond, it will become 0 because the diamond is no longer available. So usually what we'll do is we'll pass this observation, this list of numbers, to our neural network, which here is just our policy function. And it will output 2 values, a probability of going left and a probability of going right. And these 2 numbers will sum to 1 because they're probabilities. And then once we enter a new state, we'll get a reward when we enter that state, and we'll also get a done variable, which will be false if the episode is not over, and will be true if the episode has ended. And I wanted to add this little randomness element to the game so that you can still see how the policy gradient theorem even works in a non-deterministic environment, or an environment where when you take an action, you're not exactly sure what state you're going to end up in next. So first, let's just think about what is the optimal strategy for this game. And there are pretty much two possible strategies. One, you either go right all the time from this initial state to get to the flag, or you try to pick up the diamond and risk potentially falling in the fire pit when you try to climb back up the hill to get back to the flag. So the goal of the game is to maximize the total reward you receive throughout the episode. So this total reward is also called the return. And the goal is to maximize the expected return, which just means, on average, how much return we'll get if we follow that strategy. So if we look at the strategy where we always initially go right, no matter what, from this first state, the values we got out of our policy when we pass in this observation would look like this, which means 100% chance we'll go right and we'll get the flag. So the expected return with this strategy is 10, because on average, the total reward we'll get from following the strategy will be 10, because we'll get 10 every time. Now the other strategy would look like this, where we always go left from the start, then we always go right, and then if we end up over here, we'll go right again to end up at the flag. So now what is the expected return of this strategy? And there are basically two possible paths we could take. We either go left here, go right, then end up in the fire pit when we slip, or we go left, then we go right, end up on the hill, go right again, and get to the flag. So if we look at the probability of both of those paths, the probability that we'll end up in the fire pit is the product of all the transition probabilities on that path. So there's a probability of 1 times 0.1, or 10% chance that we'll end up in the fire pit, and we'll end up with a total reward of +3 initially for getting the diamond, and then -10 for falling in the fire pit, which will be a total of -7. And when we multiply those together, we get -0.7. Now, if we do the same thing for the other path, we'll see that we'll get a total reward of 3 + 0 + 10, the 0 being this intermediate state. And throughout this video, I've left all these zeros in the equations so that you can understand how the equations would work if these were non-zero rewards. But over here, our total reward would be 3 + 0 + 10, which is 13. And when we multiply 0.9 times 13, we get 11.7. So if we simplify those down, it looks like this. And when we add those together, we get our expected return of 11. So on average, we'll get a total reward of 11 with this strategy. So compared to our other strategy, where we only got an average of 10, this is the better strategy because on average, we're going to get a total reward or an expected return of 11. So that's how to think about the game. We're trying to maximize the expected return. So now the question is, how do we learn this optimal policy, or at least how do we learn a good policy? And we're going to think about this as if we were playing a video game where you start off and you don't actually know how the video game works. You don't really know what's going to increase your score, what's going to decrease your score. You don't know what these probabilities are for if you try to go up the hill. And you're just going to try to learn as much as you can about the environment by sampling episodes from it. Then you're going to try to come up with a good policy just by observing the data that you receive from interacting with the environment. And the data that you have to work with are the observations, the rewards, and the done signals. So the first thing we'll probably want to do is explore, which means we would probably want to initialize our policy so that it returns 50% chance of going left and a 50% chance of going right for any state we end up in. Then after we gain a little bit of information, we can try to improve our policy from there. However, in this example, I'm going to initialize the policy a little bit differently. I'm going to initialize it like this with these values 0.7, 0.3, 0.4, 0.6, 0.8, and 0.2. And this is just so that it makes it easier to understand what we're doing in the equations, because all these values are unique numbers, so it'll be easier to see which action probability we're talking about. So let's imagine we start off with this policy, and how can we figure out how we should change the policy so that we can increase the expected return? And to start off, let's just simplify this example down to one step. So if we look at the example now, if we go left, we're guaranteed to get a reward of +3. And if we go right, we're guaranteed to get a reward of +10. So it's pretty obvious that we're going to want to go right in this situation. But in policy gradients, what we're trying to ask is how much the expected return increases for each small change to our policy. And this is called finding the gradient of the expected return. So if we change these values in our policy, this 0.7 and this 0.3, by tiny amounts, how much will that change the expected return? So we can think about it visually like this. Here we have the blue represents the reward we'll get if we go left, and the red represents the reward we'll get if we go right. So this has a height of 3 because we'll get 3 reward. If we're going left, this has a height of 10 because that's the reward we get from going right. And then down here, you'll see the width of the blue is the probability of going left. So 0.7 for 70%. And this has a width of 0.3 for 30%. And the total area of both of these rectangles combined is the expected return. So we can see if we change the probability of going left and going right. So if we go right more of the time, eventually if we go right all the time, our expected return will be 1 times 10. If we're going left all the time, our expected reward will be 3. So the amount the expected return will change when we change these probabilities can be visualized by this orange box. So if we move this probability line to the left, we'll increase our expected return by the area of this orange box, which will be dx times 7. Or instead of looking at this difference, we can think about how each of these individual rectangles would change for each small change in their probability. So for the probability of going left, for each increase of the probability by dx, we would increase the expected return by 3 times dx. And for this red rectangle, for each increase in its probability by dx, we'll increase the expected return by 10 times dx. And then we could just cancel those out to find the difference between them, which would be 7. So now that we have that visual concept of what the expected return looks like, let's think about what would happen if we tried to calculate the gradient of the expected return. So the expected return is the sum of these two values here. So we have a 0.7 probability of receiving a reward of 3, and we have a 0.3 probability of receiving a reward of 10. We add those together to get our expected return. And now what happens if we take the gradient of this value with respect to these action probabilities? So first, we'd start backpropagating the values, and we'd get the partial derivative of the expected return with respect to this action probability, the 0.7. And to do that, we take the sum of our expected return, replace this value, the action probability, with an x, consider all other values constant, and then find the partial derivative of the expected return with respect to x. So in the slides, I use this normal-looking d letter instead of the more precise curly-looking partial derivative d letter. And so try not to get confused because this is a partial derivative, but they're pretty much saying the same thing. How much does r change with respect to how much x changes? Anyways, this is the partial derivative of the expected return with respect to this action probability. And this is how we find the expected return with respect to this action probability. Do the same thing, take the sum, replace that action probability with x, consider all other values constant, and then find the derivative of r with respect to x. Here this disappears, this just becomes 10. So now we have the partial derivatives for each of these action probabilities, and then these would get backpropagated through the neural network that produced these action probabilities, and we would get gradient values on the parameters of our neural network. So we'd get gradient values on the weights and biases, what other parameters we used to calculate these action probabilities. And then once we had those gradient values for the parameters in our neural network, we could update those parameters by taking a step in the direction of that gradient, and that should increase the expected return of the policy because the gradient will be pointing in the direction of steepest ascent to increase the expected return. Now, one thing I want to point out here, which might seem kind of weird, is that the partial derivative of this action value is 3. So kind of makes sense. If we increase it by a little bit, we'll get a little bit more of this reward of 3. But it seems to ignore the fact that these two values have to sum to 1. So we're kind of saying we can just increase this 0.7 and not change this value at all. And that's what this partial derivative is saying. So the question is, why does this work? Why can we just ignore that relationship that these have to add to 1 and look at these independently and then backpropagate those values through the neural network and we'll get the correct gradient? So to better understand this, I created this diagram. And this red arrow, this axis, is the probability of going left. This green axis is the probability of going right. And right now, we are at the point right here, where we have a 70% chance of going left and a 30% chance of going right. And since both these probabilities will have to sum to 1, we're going to see that the probabilities output from our policy is going to have to lie somewhere along this line, because these are all the values that add up to 1. So if we go back to this point right here, where we are currently, we can ask, and this blue axis is representing the expected return, and it's scaled down a lot more than these values, so just keep that in mind. But if we ask how much the expected return will increase for each little step in increasing the probability of going left, we'll get the slope of this line. And the slope of this line will be the partial derivative, which is 3 for going left. And it doesn't look like 3 in this diagram, but that's just because I have it scaled down. If it was more proportionate, it'd be something like this. So this would have a slope of 3, but I'm just going to scale it down so we can see a little bit more what's going on. So the slope for increasing the probability of going left is 3, and the slope for increasing the probability of going right is 10. And those are these two vectors here. This one has a slope of 10, and this one has a slope of 3. And you can see each of these arrows is just only going in the direction of that axis. So we're basically ignoring the fact that these values have to sum to 1, and we're just saying if we could increase this probability and keep the other probability the same, how would the expected return change? And then what happens when we backpropagate these partial derivatives through the neural network is it's going to figure out what the gradient is along this line. And that essentially looks like this. It'll find the plane that passes through both of these vectors. So that'll be this blue plane right here. And that is the gradient of this space. And then to figure out how changing our policy will change the expected return, we can look at how this pink plane, which extends vertically above this line, how it intersects this blue plane. And then if we add this orange line to represent this intersection, we can see what the gradient is of this line directly above this line, which is the possible outputs from our policy. And if we draw another line, which connects the tips of these vectors, given that the base of these triangles are both 1, we can see that it will be parallel to this orange line, and it will have the same length. And we can notice that the height difference for this yellow line is going to be the height of this, which will be 10, because the base has a length of 1, and over here the height will be 3. So 10 minus 3 is 7, and that's what we were getting before. How much changing our policy will change the expected return had a slope of 7, the difference between these two. And we can see that by looking at it from this angle. If we increase the probability of going left, we will decrease the expected return at a rate of 7. And if we look at it from this angle, if we increase the probability of going right, we will increase the expected return by a rate of 7. And this is really what's happening under the hood when we do the backpropagation through the neural network. It will take into account the fact that these values have to add up to 1, and it will find this gradient along the path of possible outputs from the neural network. So hopefully that explains how we can look at each action probability independently and ignore the fact that they have to sum to 1, and then you'll find this plane which kind of represents the gradient in that space, and then we can find the actual gradient of changing the policy in one direction or the other, and that will just be done automatically through the backpropagation process. So as we saw with this example, when we increase the probability of going right and decrease the probability of going left, we'll increase the expected return at a rate proportional to 7. And we also can get that value just by finding the independent partial derivatives for each of these action outputs and backpropagating that through our neural network. But we still don't know how to find the partial derivatives of these action probabilities just by exploring the environment. So to figure that out, let's go back to the full example. So first, let's ask, what is the expected return of this current policy if our policy output these action probabilities? And one way we could do that is to look at all the possible paths we could take. And we would add up the sum of the probability of taking that path and the total reward we would receive on that path. So for example, one path would be going left and then going left. With our current policy, we'll have a 0.7 times a 0.4% of that happening, and the total reward we'll receive is plus 3 minus 10. So that can be represented by this right here, and we'll get this value, negative 1.96, for this path. For the next path, we'll say we go left, right, and then the environment kicks us left, and the probability of that happening will be 0.7 times 0.6 times 0.1, and the total reward we'll receive is plus 3 minus 10. So that will be this line right here, and we'll get this value, And if we do it for all the other paths, going left, right, being kicked right, and then left, we'll get this value. For this other path, and for this path, we'll get this value and this value. And if we sum up all these values, we'll get our expected return, which is 2.636. Now, this is one way of calculating the expected return, but another way of calculating the expected return, which will be more intuitive going forward, is instead of summing over all the paths, is to sum over all the rewards. So we sum over all the possible rewards times the probability of receiving that reward. So if we look at this reward of +3, the probability that we'll receive that reward is 0.7, given a random episode. So 0.7 of the time we'll go left and receive that reward, and 0.3 of the time we'll go right and receive this reward of +10. And you can see those two values right here, 0.7 times the reward of 3, 0.3 times the reward of 10. So just after our first step, we have an expected return of 5.1. But after taking this step, we could also receive these additional rewards. So we calculate those in. We take this -10. The probability of receiving that is 0.7 times 0.4. And we add that in right here. And then the probability of receiving this reward, 0.7 times 0.6 times 0.1. We add that in right here. And for all these other rewards, we'll add them in with the probability of receiving them. Again, I'm keeping in the rewards of 0 just to show how the calculations would work if they were different. And when we add all these up, we'll get the same value for the expected return, which is 2.636. And really, these are the same sums. It's just some of these values are moved around and it's just broken down differently. So we'll be using this sum going forward. It's the sum over all possible rewards multiplied by the probability of receiving that reward. So if we actually knew what this sum is, if we knew all the details of the environment and we could calculate the sum, we could just find the gradient of this sum with respect to the parameters in our neural network, and we would know how to improve our policy. However, since we're assuming that starting out we don't know all the details of the environment, we won't be able to directly calculate the sum. And the idea behind the policy gradient theorem is that actually all we need to do is figure out how to calculate the gradient of this sum. So we don't actually need to calculate this exact sum, we just need to figure out what the gradient of this sum would be. And as we saw before, we can think of one step in the backwards pass of the gradient is finding all the partial derivatives of the expected return with respect to these action probabilities. So if we could find all the partial derivatives for each of these action probabilities, and then we could backpropagate those through the neural network, we would get the correct gradient for updating the network. So let's go back to assuming we know what the sum is and look at what the partial derivatives for each of these action values would be. So first, to find the partial derivative with respect to this action value, the 0.7, we will do as we did before and replace all the places where that value shows up with an x in the sum, and then find the derivative of this sum with respect to x. And this term right here is a constant, so it'll drop out. Then we get a 3 for this x times 3. Then we get this 0.4 times this -10 for this line right here. And you can see we get this full sum down here for the derivative of r with respect to this action probability. And now, if you want, you can pause the video and try to figure out what this sum represents. And if you're back, we can see it starts off with a 3, and then we're going to get a 0.4 times this -10, a 0.6 times 0.1 times this -10, a 0.6 times 0.9 times this reward of 0, and on, and we can see that this value is actually the expected return after having taken this action. So we're guaranteed to get a reward of 3, then there's a 40% chance we'll also get a reward of -10, a 0.6 times 0.1% chance of getting this reward, and so on. So this sum is the expected return after taking this action. So the partial derivative of this action value is the expected return after taking this action. And that makes sense. In our previous example of just this state, we were also getting the same thing, except for we were only looking at the immediate reward. But if we think about just increasing this probability by a little bit, we'll increase the expected reward by that little bit times the expected return after taking that action. So now if we do the same thing with this action probability, we'll replace its value with x, this 0.3, and then we'll take the derivative of this sum, and we'll see we also get 10. So that's also the expected return we get after taking that action. So now let's find the partial derivative of this action probability. So we do as we did before, we replace that 0.4 with the x, we find the derivative of r with respect to x, and we get 0.7 times negative 10. Now, it's a little bit different than before. This negative 10 is the expected return after taking this action, but now we have an additional 0.7. So do you see what the pattern is now? If not, let's try another example, see if we can get a little bit more insight. Here we'll calculate the partial derivative for this 0.6 action probability. We replace all the 0.6s with this x, and then we take the partial derivative, and we get this value down here, which can be transformed by pulling out this 0.7, and we get this value down here. And now do you see what this sum represents? Well, you can see if we look at this value in the parentheses, we're getting a 0.1 times negative 10, a 0.9 times this 0, 0.9 times 0.8 times this 0, and a 0.9 times 0.2 times this 10. So this, again, is the expected return after taking this action. But again, we multiply it by this 0.7, which is this probability up here. So let's look at one more example, and that's for this action probability down here, this 0.2. So we replace that 0.2 with the x, then we find the derivative of this sum, and we get 0.7 times 0.6 times 0.9 times 10. And here we see the 10 is the expected return after taking this action, but we multiply that now times 0.7 times 0.6 times 0.9. So those are all the probabilities on the path to arriving at this node. And this node is the node from which that action is taken. So the pattern is all these partial derivatives will be the probability of ending up in the node from which that action can be taken, multiplied by the expected return after taking that action. And if we think about it, that makes intuitive sense. Once we're in this node, if we can increase this action probability by a little bit, we'll increase our expected return by that little bit times 10. However, the probability that we'll actually end up in this node is 0.7 times 0.6 times 0.9. So the idea is that once we're in this node, increasing this action will increase the expected return by this much, but we'll only end up in this node with a probability of 0.7 times 0.6 times 0.9. So we multiply those together, the probability of ending up in that node, and then how much the expected return from that node onward will be increased by changing this action. And that will be the expected return after taking that action. So here's the idea. Instead of trying to find the sum that is the expected return, we're going to try to find this other sum, which I'm just going to use the symbol of y to represent. So first of all, with the sum, each of these x values, x0, x1, x2, are the variables for these action probabilities. So x0, x1, x2, x3 over here. And the number after the x is just to number that variable. It's not x times 2 here, it's just the x2 variable. So for each line of the sum, we have the probability of ending up in the node from which that action could be taken, multiplied by the average return after taking that action. So the probability we'll end up in this node is 1. That's the node from which x0 could be taken. That's also the probability from which x1 could be taken. For this line, we have a 0.7 probability of ending up in this node, from which the x2 action could be taken. Then we'll multiply that by the average return after taking x2, and so on for these other action probability variables down here. So can you guess what is special about this sum? It's different than the expected return, but what's special about it is that it'll actually have the same gradient. And we can see that by looking at all the partial derivatives for each of these action probabilities. So if we find the partial derivative of y with respect to x0, then all these other values will drop out when they're considered as constants, and we'll get 1 times the average return after x0. And down here, you can see the other partial derivatives we get when we do the other values. It's a similar process. All the other lines except for the line with this action probability will get canceled out. So if we look at the partial derivative with respect to x3, all these other lines cancel out when they're considered constants, and we get 0.7 times the average return after taking the action x3. And that's what we get down here. So these were the same partial derivatives we got when we looked at the expected return. The partial derivative was the probability of ending up in the node from which that action was taken, multiplied by the average return after taking that action. So for example, here's the sum of our expected return as before, and when we put it in this format using the x0, x1, x2, and so on, we can see that it'll look like this, with all the variables in place. And then, for example, to find the partial derivative of each of these values with respect to x3, we can see that all the other values become constant. Then when we take the derivatives of each of these values, up here we'll get 0.7 times the average return after x3. And down here we'll get this value. And as we saw before, this value on the right is the average return after x3. So we have this sum, which will give us the same gradient as the expected return. But you might be asking, what's nice about this sum? Why did we come up with this sum? And the nice thing about this sum is that each of the items in the sum only has one action probability variable in it. So this item up here only has the x0. This item of the sum only has x1. This item only has x2, and so on. And the nice thing about this is that it makes it easy to estimate this sum. And if you want, you can pause the video to try to figure out how we could estimate this sum just by sampling episodes from the environment. And now let's figure it out together. So you can see we have these average returns after taking the action and this probability of reaching this node from which the action was taken. So let's just see what happens if each time we reach an action, we add that action variable to the sum multiplied by the total reward received after taking that action. So for example, if we sample a first episode by first going left here, then right, ending up in this node down here, and then going left, we'll have reached the action values x0, x3, and x4 along that path. So we'll add each of those to the sum multiplied by the total reward received after taking that action. So let's imagine we sample another episode. This time we'll be going through x0, x2. So that's x0, x2 down here into the fire pit, and we'll add those values to the sum multiplied by the total reward received after taking that action. So after taking this x0 action, we got a reward of +3 and then a reward of -10. So +3 minus 10 here, and so on. Let's say we sample another episode where we just go right here. So that's x1 plus 10. Sample one more episode here, x0, x3, and x5. So we're going to go along this path, x0, x3, x5, and add those values to the sum. Now, what would this sum come out to be on average if we sampled a large number of episodes? Let's just say n episodes. And it turns out that on average, this sum would come out to this value. So n is the number of episodes we sampled. So on average, the number of times we'll encounter the x0 will be n times 0.7. That will be the probability of taking that action from this initial state. And then each time we see that action, we'll multiply it by the reward received after that action. So on average, when we take into account all those different additions into the sum, it would be equal to this x0 times the average return after taking that action. And down here, if we look at x3, the probability that we'll have taken an x3 in any episode is 0.7 times 0.6. And we just multiply that by the number of episodes we ran to get the number of times we encountered that value. And again, we'll end up, on average, multiplying it by the average return after taking that action. So this value is pretty close to this value, but it's not exactly the value we are looking for. So we have this additional n here. You can also see we have this additional 0.7 in this line, 0.3, 0.4, 0.6, an additional 0.8 here, an additional 0.2 here. So what are these additional values in here? Well, we can see that these are the probabilities of actually taking these actions. So we have a probability of 0.2 of taking this action of x5. So that makes sense. Up here, these were the probabilities of reaching the node from which the action was taken. However, down here, these are going to be the probabilities of actually taking that action, which will be the probability of not only ending up in that node from which the action would be taken, but we're also multiplying it by the probability that we actually take that action. So this sum is super close to what we're looking for. All we have to do is correct for these additional values. So you can see we could divide this total sum by n, the number of episodes, and we could also divide each of these action values by the probability of that action when we add it to the sum. And if we did that, we would get this value up here. So just to make that clear, let's try doing the same thing. So first, we take this episode, we go x0, x3, x4. So each time we encounter an action, we're going to multiply that value times 1 over the probability of taking that action. So x0 has a probability of 0.7 currently, so we'll add that in. and then we'll again multiply it by the reward received after taking that action. We'll do the same for these values down here, and we'll also multiply this entire sum by 1 over n. So n right now is just 1 for the first episode. And now let's take another episode. Here we're going through x0, x2, x0, x2. We'll do as we did before, and here we'll increment this value. So now 1 over n is 1 over 2 because we have 2 episodes. And we continue this for another episode, it'll become this. And for a final episode, it'll become this total sum. So 1 over 4 for 4 episodes, and we continue the pattern all the way down. And now, on average, this sum, if we have taken n episodes, will be this right here. 1 over n times the probability of taking this action, which will be n times 0.7 for this case, times 1 over this action probability, because we are adding those now to the sum, multiplied by, as before, the average return after taking that action. And that'll be the same for all these other lines as well. And now you can see this 1 over n will cancel out with these n's, and this 1 over 0.7 will cancel out with this 0.7, and so on and so on. And what we'll get is this value down here, which is the same as this sum up here. So through the process that we just did, we were able to estimate the sum just by sampling episodes from the environment. So if we can estimate this sum just by sampling episodes like that, we can find the gradient of this sum, and that will give us the same gradient as the expected return, so that we can just update our neural network in the direction of that gradient, and we'll be moving in the direction that increases the expected return. Now, one thing that you'll see done a lot in practice is that when we're building up the sum, instead of calculating this action value multiplied by 1 over the probability of this action value, what you can also do is just add the log of this x0 value multiplied by the return after that action. So this sum would become this sum down here. And it's essentially just a mathematical trick. The gradient of this value will be the same as the gradient of this value. And that's just because the derivative of the log of x is 1 over x. So just to see an example of that, again, if we took these sums and we found on average they would become these values, we cancel out the n's, and up here in this sum, these 0.7s will cancel out with these 0.7s and so on. Down here, we don't have those values, so it just becomes this value down here with all these other values, the 0.7, the 0.3, and the 0.4, still in the sum down here. But now let's see what happens when we would take the gradient. Let's look at the partial derivative with respect to x3. So up here, what we got as before would be 0.7 times the average return after x3. And we do the same thing down here. All these other lines will cancel out as before, and we'll get 0.7 times 0.6 times 1 over x3 times the average return after x3. And this x3 will have the value of 0.6, so now it'll cancel out this 0.6, and we'll get 0.7 times the average return after x3. So these two values will be the same. So if each of these sums give you the same gradient, why use one over the other? And it turns out you can use both, but the log version actually, in my tests, is computationally a little bit more efficient. And you can think about it because most of these probabilities use something like a normal distribution or a softmax function. And in those functions, we're taking a value and exponentiating it to get our probability. So when we're working with the log probability, we don't actually have to go through that exponentiation. We can just work directly with the log. So we kind of avoid a couple of those mathematical steps of exponentiating and then in the backwards pass going through that exponentiation. So in practice, you'll usually see this log version, but just know it's the same thing as what we did before by just taking that variable and dividing it by the value of that variable. And if using the log is still somewhat confusing, we'll now go over how we would implement this algorithm in practice, and I'll show you how we could calculate the gradient using both of these methods, and hopefully that will make it a little bit more clear. So to implement this in practice, we'll start by sampling episodes and collecting the data. So over here on the right, I'll have some pseudo-ish code. It'll be Python, mostly PyTorch motivated, but it won't be exactly correct because these would have to be tensors instead of just lists. But anyways, you'll get the idea. So we start off taking our first episode and we're going to sample our first action. So let's say first we go left and we end up in this state down here, and we're going to add this observation to our list of observations. Our action of going left, here left will be 0, right will be 1. We'll add that to our list of actions. We'll see we got a reward of 3, so we'll add that to our list of rewards, and that'll be all for this step. In the next step, from here we'll go right, and we'll end up getting kicked over into this state. So we'll add the observation that we started at to the list. We'll add the action we took, 1 for going right this time. We'll add the reward we got, in this case 0, and that will be done for this step. We'll take one more step, ending up down here, and we'll do the same thing, adding this observation, adding our action of going left, and adding our reward of 0. And now, since we reached the end of an episode, the done value is true, we're going to calculate the future return for each of these steps. So here the future return of this action was 3 plus 0 plus 0, so it's still just 3. 0 is this 0 plus 0, and this will make more sense in the future episodes we sample, but we're also going to increment the number of episode count to 1, because we finished this episode. So let's sample another episode. So here we're going to go left, add our observation, our action, our reward. Then we're going to go left again, and again add the observation, action, and reward. And now we'll calculate the future returns. So here, this -7 will be this 3 plus -10, and we get -7. This -10 will just be this -10 value. And again, we increment the number of episodes count. So let's sample another episode. This time we just go right. We just add that observation, our action, our reward. We calculate the future returns for each of the actions, and we increment our number of episodes. And we'll add one more episode to the list. Here we're going to go left, and then right, and we're going to end up in this node down here, and then we'll take another right. So we'll add those observations for each of those steps, each of the actions, each of the rewards, and then when we reach the end, we're going to fill in the future returns for each of the actions during that episode. So 13 is going to be the 3 plus 0 plus 10, 10 is going to be the 0 plus 10, and this 10 is just this 10. And then we increment number of episodes. So we've collected 4 episodes, and in practice, you may want to collect more than 4 episodes, but we'll just keep it simple and just work with these 4 episodes we collected. And now we'll use this data to update our neural network. So let's imagine we have a neural network. In this case, it'll just be a simple linear layer. The input will be the size of the observation, which is just 2 values, and the output will be the number of possible actions, so 2, 1 for going left, 1 for going right. And now we'll take our list of observations and pass them through our neural network. So this is a batch of observations, and we're going to get out a batch of logits, which will be the input to the softmax function to get our probabilities. So in PyTorch, instead of passing these logits directly through a softmax function, you would instead create a probability distribution. And then in this case, it would be a categorical distribution. We'll pass in our logit values, and we'll get out a batch of probability distributions, 1 for each observation. Now we're going to get the log probability for each of the actions given those probability distributions. So when we pass in our actions to this log prob method on our distributions object, we're going to get out the log probability values. So what this is doing is it's going through this list of actions, and for each action, it's looking at the probability distribution for each of the corresponding observations. So for this first action, it corresponds to our first observation. So when we input 2, 1, our policy is going to output this probability distribution, 0.7, 0.3. So we're asking to get the log probability of the first probability in this list. So it'll give us the log of 0.7. Now for our second action, this 1 corresponds to this observation. So we're taking in observation 1, 0. And that'll be this observation down here. Our policy would have output 0.4 and 0.6. So we're going to find the log probability of 0.6. Since from here, we ended up going right. We had the action of 1 after this node. So we're going to get the log probability of this 0.6 value. So this log probs variable will be a batch of log probabilities, 1 for each action. We'll then multiply that list of log probabilities times the future return for each of those actions, sum all those values together, and then divide by the number of episodes. And you'll also notice this negative out here, which just means we're going to take the negative of the sum that we usually use. And that's because in our examples, we have been assuming that we're doing gradient ascent, means we're trying to increase this value. But with most machine learning libraries, the default is to do gradient descent. So we just add a negative out front, and that's kind of like taking the value space and inverting it down. So now gradient descent would be the same as going to the same place as gradient ascent in the original case. Now if we call loss.backward, we'll backpropagate the loss through our neural network, getting the gradients on each of the parameters in our neural network. Now this gradient won't point in the true direction that increases the expected return because this is just a sample of episodes, but on average, it will point in the direction of the true gradient. So with each step, we may not be moving exactly in the direction we want to move, but on average, it'll point in the correct direction. And so they should equal out, and we should be moving more and more closer to increasing the expected return. So in this example, we're using the log probabilities, but let's look at what it would look like if we're just using the direct probabilities. So one way we could get the probabilities is just by taking the log probabilities and exponentiating them. So reversing that log to get the actual probabilities. And then our loss would look like this. We multiply the future returns by the probability divided by the value of that probability. So this detached method here essentially turns this probability into a constant in our sum. It's detaching this value from the backwards graph. So when we compute the gradient, we won't be going through this value. So it'll pretty much be the same as if this was just a constant. We just want to get the probability values and divide by them, but not backpropagate through them. So if we take these values, sum them all together, and divide by the number of episodes, then as before, we add the negative just because we're doing gradient descent. This will give us a loss that if we call loss.backward, will give us the exact same gradient as if we used this loss up here. So both of these methods work using the log probability or just using the probability, but I recommend using the log probability because it's computationally a little bit more efficient if the computations are done correctly. And you might be asking, is it just more computationally efficient because we're going through the log prob here and then we're exponentiating it? And actually, if we don't do this and instead we get the probabilities by just using the probabilities directly like this, and it's a little confusing since in PyTorch there's not a convenient method for getting the probability of each of the actions, but this code will do that. But even if we do it like this, the log probs should be computationally a little more efficient. But I just wanted to show you this other method since to me, it makes more intuitive sense. Because for each action in this sum, the probability that that action will be in the list is going to be the probability of taking that action in our environment. So here, if one of the probabilities is this 0.2, it'll only be in the list on average 0.7 times 0.6 times 0.9 times 0.2 of the time. But for the gradient to be correct, we want to actually multiply this future return value by the probability of ending up in the node from which that action was taken. So if we just divide this value by the value of this action detached from the graph, so it's just a constant, we're not going to backpropagate through this value, then that kind of gets us back up into the probability of ending up in this node. And then we'll multiply that by the future return to get the correct gradient. And when you use the log probabilities, it's just a convenient way of doing the same thing that's also computationally a little more efficient. Now, this is a very simple version of what some people call the vanilla policy gradient algorithm. And it's just vanilla because it's very simple. And you can start adding on more bells and whistles to, for example, reduce the variance of your gradient or to make the step size of your updates more consistent. And I just want to show you one of those little tricks that's frequently done just so you have an understanding of what it's doing. So we'll start by going back to this version of the algorithm where we're using the log probabilities. And now let's ask, how consistent is the size of this loss going to be? And how much is it going to vary depending on the environment? So usually when we're training a neural network, we want a somewhat consistent step size. If the steps are too big, then our network may not converge. And if the steps are too small, it may take too long for the network to converge. So we want this loss to be somewhat consistent between the different environments we could train on. So one thing you'll notice is that in this loss, we're multiplying by this future returns variable. And if the rewards in our environment are really big, for example, for if when we take one step, we get a reward of plus 1,000. If we take another step, we get a reward of negative 1,000. Then this loss could be really big in the positive or the negative direction. We may be taking huge steps just because that's how the environment was set up with the rewards at that scale. Now, in another environment, the rewards may be scaled down to be within 1 and negative 1, and we may be getting very small rewards, so 0.1, 0.2, and that would make this loss very small. So the first idea is to make these future returns more consistent is we can normalize them. And that looks like this. We're going to find the mean of the future returns, we're going to find the standard deviation, and then we're going to take the future returns, subtract the mean, and divide by the standard deviation. And we clamp by this very small value just to protect against the case where all the values in our list of future returns are the same, which might happen if we have an environment with very sparse rewards, and we may have a batch of episodes where we don't receive any rewards throughout all of the episodes. So in that case, the standard deviation would be 0, and when we take the future returns and subtract the mean, this value will be 0, and we would have 0 divided by 0 if we didn't add this clamp. So to protect against that, we just clamp using this minimum value so that it would be 0 divided by a small value, and we'll get 0 over here. Then instead of using this loss, we're just going to replace our future returns by these normalized future returns down here, and we'll use this loss instead. Now the question is, how can we subtract by a value and divide by a value and still expect to get a gradient pointing in the same direction? So first, let's look at subtracting by the mean. So what this essentially is doing is subtracting all our future returns by the same value. So for example, if the mean of our future returns is 5, that's the same as saying, let's add a reward of negative 5 to the end of all of these paths. What that essentially means is that it doesn't matter what you do, no matter what, you're going to end up getting an additional reward of negative 5. So if there's nothing you can do to avoid that reward or increase the probability of getting that reward, then that won't change the gradient, because the direction that you should improve your policy before that reward was even present will be the same direction that you should improve your policy now that that reward is there. It's basically a value that on average will get canceled out and not have an effect on the gradient. So subtracting by the mean won't change the gradient in expectation. However, because our future returns were sampled from the environment, it may have an effect on this particular gradient step. But the idea is that on average, it won't have an effect, so we can subtract by this value, and on average, we'll still be moving in the true direction of the gradient. Now to look at dividing by the standard deviation, this will just scale all the future returns by the same amount. So it may scale down our gradient or it may scale up our gradient, but it will still point in the same direction. It'll just have a more consistent size and not depend as much on the size of the rewards for this specific environment. So while that has helped with the fact that different environments can have different scales of rewards, what's something else that can vary between environments? The length of the episodes. So in some environments, the episodes may be really long, where you take a lot of steps, and in some environments, they may be very short, like in this example, where the maximum steps are 3. And if you look at our sum down here, you'll see that we're dividing by the number of episodes. So let's say we sample 1,000 steps. If the average length of an episode is 100 steps, then on average, this num episodes value will be 10. However, if on average our episodes are only 10 steps, then on average this num episodes value will be 100. So that will change the sum of this value by a factor of 10. So when we have longer episodes, on average, this value will be larger, a larger positive value or a larger negative value. So can you think of what we can do to make the loss value more consistent and depend less on how long the episodes are on average? And the idea is that instead of summing these values and then dividing by the number of episodes, we just take the mean of these values. And essentially what that's doing is also dividing by the average number of steps. So if we look up here at our original sum, we took the sum and then divided by the number of episodes. If we also added to divide by the average number of steps per episode, we would end up with this value right here, because the number of episodes times the average number of steps per episode is, on average, going to be the total number of steps in these tensors. So when we take the mean, it's the same as taking the sum and dividing by the total number of steps. So since we're essentially just dividing by the average number of steps per episode, that's going to have the same effect as just dividing by a constant, which on average is just going to scale our gradient, either scale it down or scale it up, but it's still going to point in the same direction. And now, regardless if our environment has long episodes or short episodes, we'll get a more consistent loss value, and we'll take more consistent size steps in our policy updates. And just to clarify, when I say that these two changes don't affect the direction of the gradient on average, the two changes being normalizing the future returns and dividing by the number of steps instead of the number of episodes. What I mean is that these two changes won't affect the direction of the gradient as the batch size increases to infinity. But in practice, since we're sampling a finite batch size, these two changes will not only affect the direction of the gradient due to variance, but also due to correlations in the sampled episodes. For example, correlation effects between episodes that have higher or lower than average variance in the future returns, or episodes that have higher than average or lower than average number of steps per episode. However, in practice, these two changes usually end up having a beneficial effect. But just note, if you have environments that have a high variation in the future returns or the episode length, it may be beneficial to increase the batch size to make the direction of your gradient more consistent. So to make it even more clear, here's an outline of what an implementation might look like. We start by initializing our neural network. We'll create an optimizer and register the parameters of our neural network with that optimizer. And then in a loop, for however many iterations we want to update our policy, we will first collect multiple episodes of data. I don't show the code of doing that here, but what we'll end up with is a collection of observations, actions, rewards, and future returns. And you'll notice we don't actually use this rewards value anywhere down here in the code, but I just wanted to show it here because usually we use it to calculate the future returns. So then we'll pass our batch of observations through our neural network to get our batch of logits, and then we'll create a batch of distributions for those logits. Then we'll get the log probabilities for each of the actions in our batch of actions. We'll then normalize the future returns to get our normalized future returns variable down here. We'll then calculate our loss as we did before, and we'll zero the gradients in our neural network, backpropagate the gradient of the loss through the neural network, and then we'll tell the optimizer to use those gradient values to take a step to update the parameters in our neural network. And we'll do that in a loop. The next time through, we'll collect a completely new set of observations, actions, rewards, and future returns from sampling episodes from our environment. And we'll do all these steps over and over, slowly improving our policy in the direction that increases the expected return. So the key insights are that instead of finding this sum that is the expected return, we find this other sum, which just has the same gradient as the expected return. And we find that sum by sampling episodes from the environment. Then we use that alternative sum to calculate the gradient values for the parameters in our neural network, and on average, they'll point in the direction of the true gradient of the expected return. And the other big insight for me was just that I can see that the sum of values are just the probability of actually taking that action, and then we're essentially dividing by the value of that probability to get back up into the probability of ending up in the node from which that action was taken. And then we multiply that by the average return received after taking that action. And that visual of going down into the graph, dividing by its probability to go back up to the node from which that action was taken, and multiplying that value by the expected return after taking that action really helps me have a more intuitive sense of why that sum gives us the correct gradient for increasing the expected return. This was a long video, but I hoped it gave you a better intuition for the policy gradient theorem, and instead of just seeing it as a couple math operations that lead to this equation, that you can see the actual visual of going through the tree structure of an environment and how we're getting the values that we are. So that's all for this video, but I'll be making more machine learning related and reinforcement learning related videos. So if you're interested, feel free to subscribe, and I will see you guys next time.